All right, let's get started. Sorry, a little bit late start today. So we are looking at electric charges and the forces due to electric charges, and today we're also going to be talking about electric fields. So let's start off and get to the homework, and let me grab, let me grab the assignment here. I think this is what you guys had, right? Let me see. No, this is the second one. Let's go back to the first one. So we had two assignments and just looking at a couple problems from each of them. So only 3 problems, but some of them involve more than one part. All right, so here we go. Let's do, so number 2 first. Hi, Adam and Monty. Good to see you guys here. Let's look at these. I know Adam had a question on, basically it was number 1 on the second part. And I think, so if you look at the sample problem, it was really, really complicated because they weren't all in a line. But I think the problem I assigned you guys, they were all in a line, so it wasn't so bad. But we'll get to that here in a second. I want to start with number 2, and then we'll get to the second section in a little bit here. Okay, so we got 2 identical conducting spheres placed with their centers 0.3 meters apart, and then one is given a charge of that, and the other is given that charge. We want to find the electrical force exerted on one sphere by another. So the 2 forces are going to be equal but opposite. And we know that already from Newton's third law, right? So when you have the forces always come in pairs, and so that's the 2 forces are going to be equal in magnitude but opposite in direction. All right, so let's go ahead and solve for, well, what is that magnitude of the force? So 2a, we're going to be looking at a force caused, and this is known as Coulombs Law. So the force is equal to this Coulomb's constant, and I'll just write out the equation first, times the 2 charges. So Q is a charge, so this is charge 1, that's charge 2, over the distance between them squared. All right, so that's your equation that we're going to be dealing with, and we're going to go ahead and just plug in the numbers. And we have to keep in mind that the value of this is going to be negative, such that if you have different charges there, you're going to have a positive force, an attractive force. If you have the same charges there, then they're going to end up being a repulsive force. Okay, so let's go ahead and do that. All right, so this is back over here. Find the electric force exerted on one. All right. Your value of Kc is Q1 is 8.99 times 10 to the 9th, I think. Yep, and that's going to be newtons meters squared per coulomb squared. The units are going to be important here. We're going to make sure we keep our units the same, especially because some of these deal with centimeters. I don't think there's any centimeters here. We have to worry about those things, the micro coulombs there, all that kind of stuff. So we have here Q1 in this case, and it doesn't really matter which one's which, so we're going to put that 12, positive 12 times 10 to the minus 9th coulombs, and this is a negative 18 times 10 to the minus 9th coulombs, and then we should have a negative out here to give us a positive value if it's attractive, although you can have it the opposite way. And we have a distance of 0.3 meters. All right. So that's going to be 12 negative 9 times 18 negative 9, all divided by 0.3 0.3 squared. Okay, and then we're going to multiply by our constant here, 8.99 times 10 to the 9th. And that's going to get us 2.16. Times 10 to the minus 5. Now, what are the units here? So we have kind of really, really small numbers here, negative 9th, negative 9th. And so that's why we're getting such a small number here, right? And you can imagine one of these 10 to the minus 9th, one of these 10 to the minus, this 10 to the 9th, we're going to cancel out, and you're going to have 10 to the minus 9th on top, which is going to get a little bit bigger because you're dividing by 0.3 squared, which is going to be a small number. But this is what you end up with. Now the units are going to be your Coulomb squared on top over Coulomb squared on the bottom cancels out. Your meter squared over meter squared cancels, and you're left with simply newtons. So a fairly small force. And that's to be expected because our charges are fairly small. So let me see, our 1 and 2 E and P respectively. E and P? E and P. I'm sorry, I'm not with you here. Is the force negative? The force is, and I've learned this, I've learned this different ways. Basically, the most important thing is the force is attractive. Okay? 1 and 2, electron and proton. No, these are not electrons and protons, right? Electrons and protons. No, we're going to talk about electrons and protons, but these charges are much bigger than an electron charge. And yeah, and we're talking about distances. So these are not electrons and protons or anything like that. But back over here. So we have, is the force negative? The way I'm gonna write these is that it's gonna be positive. I'm gonna keep this as a negative value. From what you've seen, they're in the same position as the charges of the electrons and protons. In the same position. Really? In the equation. Electrons, which equation are you talking about relating this to electrons and protons? There is, this is the general, so this is generally Coulomb's equation, which is for any charges, whether we're talking about electrons, protons. Oh, the one in the practice problem. Oh, yeah. Okay, wait, I was lost there because I'm looking at number 2 here. So the one in the practice problem, yes. Yeah, there's an electron and proton in that one, in the practice problem. And yes, that's going to be your Q1 and Q2 in that case. Okay, sorry. Yep. I didn't know you were talking about the practice problem. That's why I was totally lost on that one. Right. So I'm going to put this as a positive force and just essentially making this equation such that it's going to be positive when they're attractive, negative when they're not attractive. But what's more important is you understand that when they're opposite charges, these things are going to attract. Okay? So I think some people might do it differently, but this is going to be the force is attractive. Okay? Or you could have it as negative. So if we put this as positive and we put this as a negative as an attractive force, that's fine too. I'm not going to really worry about positives and negatives on these particular problems. If we had them in like specific locations, we need to make sure we know what direction they're going, left, right, or whatever, but it is an attractive force. And so the two forces, these two objects are being attracted together. Okay, so B, the spheres are connected with by a conducting wire after equilibrium has occurred. So equilibrium, so we've seen this term a whole bunch of times. Here for electrical equilibrium, or even for thermal equilibrium, but for electrical equilibrium, it means that they have the same charge. So once they're connected through a wire, so a conducting wire, that means electrons can flow from one side to another, so that they should, electrons will flow until they have the same charge. So once they have the same charge, then the thing's not going to have a zero force, but it's still going to be a force because the two objects do not have the same charge initially, okay? And so let's just have a little diagram of this. You have over here, this is Q1, and over here you have Q2, and let's move this up a little bit. Let's just do it like this. Okay, so you have Q1 and Q2. They're still separated by a distance of, we said 0.3 meters. And if initially this one is 12 times 10 to the minus ninth, it's a positive. And this one was negative 18 times 10 to the minus ninth coulombs. How, what's the charge once they're going to be both exactly the same charge? Well, the simple way to do it is you'd add these two together and divide by 2, and that would be the total charge that each one would get. The total charge you have, right, is 12 and negative 18. That's going to be a negative 6. And so after they reach in some sort of electrical equilibrium, they're going to have now charges of negative 3 times 10 to the minus 9 coulombs and negative 3 times 10 to the minus 9 coulombs, right? So that the total is always going to be the same, because you can't, in this process, you're not gaining or losing electrons or gaining or losing charge. You're just having a flow from one to the other. So you're going to end up with negative 3, negative 3. All right. So questions here. Let me see if... Right, it's just the charged items. So I think we got that clear. I just noticed that one question now. All right, so in this case, it's still going to be the same equation. How do we get this in a calculator? Hi, so we're going to get this in a calculator. I'll show you how we do it again for this problem. So our force in this case, and let's use a different color in this. So our force is still going to be equal to this 8.99 times 10 to the ninth newtons meters squared per coulomb squared. And then we're going to multiply that by the charges, which is negative 3 times 10 to the minus 9 coulombs. And in this case, the other one has exactly the same charge. So it's just going to be this squared and all divided by, once again, 0.3 meters squared, r squared. So the way I'm going to put this in my calculator is going to be like this. And you can even, if you want to, you could store this value in your calculator, this 8.99 E9. You could store that as, let's say, maybe C, right? Just like I've done for other things in the past, like, for example, I got R for the gas constant. You can store those in your calculator. So I've got C now stored in my calculator, 8.99 times 10 to the ninth. That's our value, your Coulomb's constant. And so let's go ahead and do that. So how do I put this in my calculator? Just do C times, in this case, we're going to put negative 3 to the negative ninth squared divided by 0.3 squared. And that's going to get us what? Well, that's going to get us 8.99 times 10 to the minus 7. The units must be newtons. Now, it's important to note positives and negatives. Again, it really depends on how you do this. If you do positive as an attractive force, this will be negative, but I don't really care whether you put positive or negative. What I want you to tell me that this is going to be a repulsive force. Repulsive force because they both have exactly the same charge, right? They're both a negative charge, so negative and a negative are going to repel each other, so this is a repulsive force. This is a much smaller force than initially, and we're to expect that it's a smaller force, right? Because the absolute value of their charges decreases significantly when they reach equilibrium. So 12 and 18 going down to 3 and 3, so we'd expect a much smaller forces, and that's exactly what we find. Okay? All right, so next up, number 3. We've got 2 stationary point charges of 60 microcoulombs and 50 microcoulombs. They exert a repulsive force on each other of this. So now we're going to have to rearrange the equation some. Okay, so again, we got the force, and that's going to be equal to this times Q1, Q2 over R squared. And in this case, what are we solving for? What is the distance between the 2 charges? The distance is going to be R squared. So we want to, or the distance is R, so we want to solve for R squared and then figure out what that is. So let's multiply both sides of the equation by R squared first. That's going to get us F R squared equals KC, Q1, Q2. And we're going to divide by F, so that's going to get us R squared equals KC, Q1, Q2 over F. And we can go ahead and then solve for R, which is going to be the square root of KC, Q1, Q2 over F. Now, obviously, we're going to need to worry about negatives. Now, this is first year chemistry, or first year physics. We're going to need to worry about negatives. If we end up with a negative value in here, we're going to need to make it positive, because of course, where this, this force or something could be attractive or repulsive, we need to have a positive value in here so that we get a real value for R. All right, so let's go ahead and plug in some numbers. So R is going to be the square root of 8.99 times 10 to the 9th. That's our constant. And then our charges of 60. And be careful with these symbols here. That's 10 to the minus 6, that micro. So we have 60 times 10 to the minus 6 coulombs, and 50 times 10 to the minus 6 coulombs, all over a force of 175 newtons. That is a significant force, right? So much, much greater than we had in the previous problem. 175 newtons. But we'd expect that because we now have much larger charges. And so what is that going to end up being? Okay? So you don't even need to worry about positives or negatives. The whole thing must be positive, so we can leave everything positive. And that makes sense here. We can just check, right? That's a positive charge, that's a positive charge, and it says there's a repulsive force. So that makes sense, okay? The only way you could possibly have a negative inside here would be, let's say you had these two were the same and it was, let's say, attractive, which of course doesn't make any sense, okay? If they're the same, it's going to be repulsive. If they're opposite charges, then they're going to be attractive. But you don't need to worry about that because there's not going to be any kind of trick question for those kinds of things. All right, so let's do this. All right, so we have C, which is going to be our Coulomb's constant, times 60 times 10 to the minus 6. That's the micro coulombs, times 50 E negative 6. And problems like these, again, I highly, highly recommend you guys use E, because if you use times 10 to the, you're going to end up with order of operation problems or order of operation difficulties in your calculator, okay? So make sure you use the E symbol. It'll go down much, much better. Divided by 175, and we get out this number, all right? Let's take the square root of that, and we get out, well, look at that, just 0.39. 0.39 sig figs. We actually have 3 significant figures because this is 60.0. So 0.393, And what are the units for R? Well, like always, your units for any kind of distance are going to be meters. Because, well, how do we know? We go back to the units for your value of Kc, right? So Kc is going to be 8.99 times 10 to the ninth. And the units are going to be, for that one, newtons, meters squared per coulomb squared. And we notice that we have coulombs in each of these, and so they're going to cancel out, and we're going to be left with meters, right? Newtons over newtons cancel. All right? So guys, questions on any of those problems before we get to the more challenging one? Okay. So let's go ahead and move forward then. We have, what do we got? Just one page over, we're going to look at practice. All right, there we go. We have problem number one on this one. We're not going to get into the whole, I mean, we could, but we don't want to get into trigonometry and worrying about angles and all this stuff. And so I didn't give you number two, or we didn't look at the sample problem for this one. We don't really want to bother with that. There's no point. I know you guys know how to do it, and we don't want to spend all the time working with triangles for these. So we're just going to deal with multiple charges on a single line rather than in two-dimensional space in different locations. Okay, so this should be much, much easier because they're on a single line and we don't need to worry about figuring out all these different angles and all that kind of stuff. Okay, so let's just go ahead and do this one. So we have 3-point charges, and it's probably valuable to go ahead and draw it out so that you know exactly what's going on here. All right? Because if you don't draw it out, you might be a little bit confused. So they lie along the x-axis. So they're all along a single axis, right? And it doesn't really matter exactly if you draw this to scale or anything, but you have one at x equals 0. And let's find out what that one is. So we're going to say Q1, the one at x equals 0, just make sure this is right, is going to be 6 microcoulombs. 6 microcoulombs. And then one at 3 centimeters. We'll just put that, this is a good spot, right there. 3 centimeters. And this is going to be 1.5 microcoulombs. And then another one at 5 centimeters. A little bit closer. I think that's it's not drawn to scale, whatever, which is -2 microcoulombs. Okay, so keep in mind this value here is a distance of 3 centimeters or 0.03 meters. Okay, let's just stick in the SI units of meters here, and this one going from 3 to 5 is going to be 0.02 meters. All right. Is there any other information that we need here? I think that's the situation. So it's very, very, very useful to have this drawn out here. All right. Is the one you did before this, why did you write the force as MC? Did I write the force as MC? Maybe I made a typo. So F, that's an F. F, the one here, F. Sorry. Before the last problem on that page, I don't know if I have B, this one here, force. So force in newtons. Force is, you talked about so this is newtons meters squared per coulomb squared. And then this, I kind of ran out of space here. This should be over here. And so this is coulomb squared, meters squared. This is 0.3 meters. The answer of 3. Oh, the answer of 3 down here. The answer of 3 was 0.393 meters. Right? I was looking in the wrong spot. Okay, so yeah, down here, this is the value of Kc. Okay. Okay, cool. All right, let's come back over here. All right, so here's our situation. We've got 3 point charges, positive, positive, and negative, and we want to deal with, and I think that's the whole situation here, right? So we need to calculate the magnitude and direction of the electric force on each of these 3 point charges. And so that's, it's a significant amount of work already, but the nice thing is that each of them is on a line, right? If one of them was not in this line, it would make our lives a little bit more complicated, because then you'd have to deal with the trigonometry of adding those. But because this is one-dimensional, right? This is honestly just a one-dimensional problem. We don't have to deal with any kind of trigonometry. We just have to add them together, simply positive, negative, and that's it. All right, so let's go ahead and do this, and let's just start over here and work our way down. So this is going to be 0.1, 0.2, 0.3, and so let's see, let's just calculate the, let's just calculate the charges, or let's just calculate the forces on each of these points. So let's start with 0.1. Okay, so 0.1, we'll call this 1, 2, 3. Right, so the force of 0.1 is simply going to be the different forces all added together. Okay, so the force at 0.1 or on 0.1, or the force exerted on this one particular point, and I'm going to go ahead and just move the problem out of the way and leave this here, is going to be equal to, and let's just write up the equation here. That's going to be the equation for all of them. So that's going to be Kc, which is going to be Q1, Q2 over R squared. So this is going to be Kc, and you're going to have in both these cases, it's going to be the Q1 here, and we could do it like this. We can do it as, well, let's just do it the long way, and then I'll show you how we can shorten it on the next one. So we have a 6 times 10 to the minus 6 coulombs times 1.5 times 10 to the minus 6 coulombs, divided by the distance between them, and that's going to be 0.03 squared. And then we're going to add to that, or in this case, we're going to subtract the charge of the force of this point on this point. So that's going to be 6 times 10 to the minus 6 coulombs times negative 2 times 10 to the minus 6 coulombs, all over a distance of 0.05 meters squared. All right. Now we need to keep in mind that the force between these is repulsive and the force between these is attractive. And so now our signs are going to be pretty important, okay? And so we'll just leave positive as repulsive and negative as attractive. And again, it doesn't really matter which one's which, as long as you are consistent with this throughout the problem. So we'll go ahead and factor this out, the K value out, and multiply that through that at the end. So we're going to have 6 e negative 6 times 1.5 e negative 6. All right, that's going to give us a positive value divided by 0.03 squared, right? And we need to, and I can go ahead and calculate that then. And we're going to subtract from that 6 e negative 6 times 2 e negative 6, all divided by 0.05 squared, right? And so we're going to end up with this value right here, but that's not the end. We need to multiply by our constant, our Coulomb's constant of 8.99 times 10 to the 9th. And this is what we get out, 46.7 newtons. 46.7 newtons. Now let's pause and think for a second. Okay, well, is that going to be attractive or repulsive? And what we did was we said we left this as positive, so that was going to be a repulsive force. So positive is a repulsive force, and then we subtracted out that attractive force, and the attractive force should be less than that. Well, why is it less? The charge of this one is more than the charge of that one. The absolute value of the charge of this one is more than the absolute value of the charge of this one. So why in the world would it be repulsive rather than attractive? Well, the reason is because this one is so much closer than this one. And because the distance here is squared, that repulsive one is going to have a greater impact on what's going on. And so this is going to be a repulsive force. So we'll go ahead and leave positive as repulsive and negative as attractive there without changing any of those signs. So we're going to do this with all three of them, all right? And that's going to, we'll do that middle one next. So F2. And we're just going to multiply by the Kc at the very end. It's just going to make it a little bit easier. Although, honestly, not that much different. Is going to be 6 times 10 to the minus 6 coulombs times 1.5 times 10 to the minus 6 coulombs. And this is going to be the same as this one above. But this one's going to be different. Right? Plus 1.5 times 10 to the minus 6 coulombs times a negative 2 times 10 to the minus 6 coulombs. So we're dealing with these. So this first part is the attractive or the repulsive force between these two, and this part is the attractive force between these two. Now, keep in mind the distances here are not going to be the same in every single problem. This distance is now going to be 0.02 meters squared. All right? So it's so easy to get confused as to what's what. Notice in this case, these two terms are the same, but these two terms are different. Why? Because we're taking the point of view of this point, and so obviously this is going to be the same, but this is going to be different from that. All right? So we have now a repulsion between these, an attraction between these. All right, so what's going to happen here? We have, let's plug these in. It's going to be 6 e negative 6 times 1.5 e negative 6 divided by 0.03 squared. And we're going to add to that this negative value, so subtract 1.5 e negative 6 times 2 negative 6 divided by 0.02 squared. And we're going to get out this value right here, 2.9. Let me see. We're going to get out 2.5 times 10 to the minus 9. And we forgot we got to multiply by our constant here, which there we go. So 22.5. F2 equals 22.5 newtons. All right, so what's going on? What do we do in terms of the direction on these? And the first one we said, well, that was repulsive, and that was a positive value, okay? And so let's make some sense of that. So that repulsive force means that this is being repulsed by overall these. So it's going to be repulsive, which means it's going to go to the left. Now we're still getting a positive value. What does that mean? We got to pause and think about it, okay? So this value of 1.5 times 10 to the minus 6 coulombs is being repulsed by this one and is being attracted to this one. And so it's clear in this case that it's going to be moving, what? It's going to be moving this way. Okay, so both of these forces are going to be acting on it so that it moves to the right. And in fact, let me see. This is going to be actually, and I'm sorry about this, but there's a mistake. I don't know if you guys caught it or not. So this force, so if I'm looking at the perspective of this one, and this is where the signs can really mess you up. If you stick with the signs, you can still get messed up. So this one is a repulsive force, which pushes this one to the right. This one is an attractive force, which pushes this one still to the right. So what I did there, when I subtracted, I shouldn't have, right? And that's where I was saying before that the signs of these is really going to be a relative thing. So let's go back and adjust that. So it should really be, let me go back to the first one. So it was this, and then rather than subtracting, so if we did this before, where we subtracted, this actually should be added. We should be adding this term here rather than subtracting. This needs to be added to this. This should be counted as a positive. Well, the charge is negative. What's going on? In reality, this is being moved to the right by both of them. So the two forces are adding together, and the force is definitely going to be to the right. So this is going to be times C here. And that's going to be not 22.5. That was wrong. So it's really, really sorry about that, guys. It's actually going to be 157 newtons, okay? Because both of them are going to the right. All right? All right, so really, really tricky thing here on the charges. It even got me there for a second. I'm so sorry about that, guys. But yes, this is a negative and this is a positive charge, but keep in mind the big picture, okay? Both of those charges, how do they affect this central charge? Both of the charges force this charge to move to the right, right? This is being repelled by this one, so positive force to the right. It's being attracted to this one, so that's going to give us another force to the right. So those two forces must be added together. All right? So these things can be so tricky. You've got to be thinking about actual directions and rather than just positive and negative. All right? Is it repulsive too? So no. So this is actually repulsive and attractive. And when you have multiple charges like this, you can't just say repulsive or negative. Or repulsive, you can't just say repulsive or attractive, because this one here in the middle is being repulsed by this and attracted to this, but both of those are going to add together to make it an overall force to the right. All right? And so that's going to be 157 newtons to the right. So guys, really sorry about that. And you can see immediately how tricky these things can be just looking at the positives and negatives. Think about them separately. Think about what each of these forces is going to be doing. They're all going to be pushing this one central one to the right. And so this is now correct. All right? And so we had to actually make this count. So what we should have actually done is, let's say, subtract the negative. But you need to think about, okay, are these two forces repelling each, or going the same direction or opposite directions? In this case, those two forces are going the same direction, so that they should be added together. In this case, it's repelling this one, but attracting that one. All right, so moving on to the last part, or the last one, F3. Same thing. So we have Kc, and that's going to be your 1.5 times 10 to the minus 6 multiplied by, let's do this one first. Sorry. So 1.5 times 10 to the minus 6 times this 2 times 10 to the minus 6 over what? That's over 0.02 squared. And this is what I'm going to do. Rather than making it negative or positive, I'm just going to leave this as positive, and I'm going to think, okay, how is that going to be affected? That force is going to be attractive, so it's going to cause this one to be attracted to the left. It's going to be pushed to the left, right? And so then I'm going to add or subtract, I'm going to determine at the end, and so that's going to be the next one is going to be these two, which is down here, 6 times 10 to the minus 6 times 2 times 10 to the minus 6 all over their distance, which is 0.05 squared. All right, and so what's that going to do? It's going to be, this is negative, this is positive, so that's going to be attractive. So this and this, so negative, positive, that's going to be going to the left. All right? And so a force to the left and a force to the left, we need to, because both of these forces are going to the left, we're going to add them together. Okay? And so when we add them together, those two forces are going to add together and push it to the left. And how do I know that? I know that simply by looking at this diagram and saying, okay, this is a negative and these are both positive. So this negative is going to be attracted to that one and it's going to be attracted to that one. And so those two attractions are both going to be going to the left. All right, so let's go ahead and do the math here for our final problem. It's going to be 1.5 e negative 6 times 2e negative 6 divided by 0.02 squared. And we're going to add to that 6e negative 6 times 2e negative 6 all over 0.05 squared. All right, and we're going to get out this number, multiply that by our constant. Remember, our constant is going to be 8.99 times 10 to the 9th. And that gives it 110, rounded up, so 111. And our direction is going to be to the left. All right. So guys, that last problem, that was definitely a little bit more challenging than I realized at first, right? But actually it wasn't so bad. Imagine how bad it would have been if they're actually in three-dimensional space. Then you have to worry about angles and all that kind of stuff with the forces. But this is just a one-dimensional aspect when we have three different point charges. All right. Now, guys, any questions on those? And the lesson that I learned from this is we have to really, really think about the direction of all of these, right? Rather than just thinking of attractive and repulsive, we need to really think about the direction. Is this going left or right, up or down, that kind of thing. Okay, so really, really think about those. When they're going the same direction, the forces are going to add. When they're going in opposite directions, the forces are going to subtract. Okay? So let's see. I'm going to let you guys, if you guys have any questions, we can ask. And I'm going to give you guys the homework. The homework is going to be, let me see, page 914. So we're not going to do problem, what is that? What chapter is this? 16? We're not going to do 16C. We're going to skip over to 16D, which deals with electric fields. And we're going to do just sample the practice problems 2 and 3. So that's page 914, sample problem D, and then the practice problems 2 and 3. All right, question. not to sound entitled or anything, but normally people follow that by a but, and then they say something. Yeah, what's up, Jeremiah? I think we should have done an introductory lesson. Oh, I didn't see that. You think we should have done an introductory lesson to that? Yeah, good call. You're totally right. Yep. Yeah. Cool. All right, are we good so far? Any other questions? Okay. All right, I'm going to sign out. Do we have to read anything? Yes, it is just the next section on electric fields, page 911 and 920. I'm going to put it all in Google Classroom right now so you guys can see the page numbers and all that kind of stuff. Okay?